Hello, my name is Edgardo, and this is my final project, music generation using Google Magenta. Automated music generation is still to this day a great challenge. The latest advances in machine learning and deep learning have produced interesting results, but most of them are limited to monophonic music generation without sound dynamics. Google Magenta is a research project from Google Brain in machine learning and deep learning for creating art and music. The newest performance RNN model from Magenta is aimed to more natural polyphonic music generation, including dynamic expressions. I wonder if I can apply the performance RNN model with dynamics to generate music in the style of one of my favorites, Beethoven's piano sonatas, and how much of this process can be done using Google Colaboratory. I will explain the steps I follow to complete my project, the required software, the dataset creation, the model architecture, the train and the testing of the model, the visual results of the training, and finally generating music. My hardware environment is a MacBook Pro from 2009. The required software. The required software is Anaconda Python, at least 2.7, with Jupyter Notebook and TensorFlow, Google Magenta, Bazel, Google Colaboratory. I installed the Anaconda for Mac OS with Python 2.7 and 3.6. I installed the Magenta environment and Anaconda. After trying all the options, the easiest one was to do the automatic install for Anaconda. I installed some other packages like RMIDI and some other required packages like Pandas, Matplotlib, SciPy, and also cloned the Magenta library. I installed Bazel for macOS. I also installed the Magenta environment on Colaboratory. Actually, the configuration for Colaboratory was much more simpler than the Anaconda. I installed some packages and some needed libraries. I also installed some other packages to give me access to Google Drive to use it as a repository. The big dataset. A good source for data for this project is the Yamaha ePiano competition website. There I found real performances from the Yamaha ePiano competition, about 1,400 independent MIDI files of performances by skilled pianists. The files are organized as independent performances files and can be downloaded individually in 3 different formats: as a standard MIDI file, as a MIDI extended format, or as an e-sequence. For this experiment, instead of downloading a bunch of random files, multiple files of different performances but of the same piano sonata were downloaded. Since I wanted to train the model in a very specific style of melody, I decided to grab as many files as I could of the same Beethoven sonata to train the model. The files used for this dataset are all in standard MIDI file format. In the standard MIDI file format, all the data is organized as chunks. Each chunk represents an event that happens at a certain point in time. These events can be related to notes, like note on, note off, or related to controls, to nuances, like a change in volume or pressing a pedal. In example, here we can see one of the data files and how the events are organized. The piano roll file format. Traditionally, machine learning and deep learning applications use the piano roll format. The events of a note on and a note off are converted to a single note line, with a duration of seconds defined by the original MIDI events of note on and note off. This is easy to encode as one hot, since the piano roll can be divided in slices per second, and depending on which note is on or off, then we can generate a one hot vector per each second. This basically turns the schema into a classification problem of 88 classes, which correspond to the 88 notes in a keyboard. The issues with this approach are that even the model can deal with polyphony, it ignores all the musical nuances, like accents, changes in volume, sustain, etc. Also, it is required that the melody is quantized to match to the precise second. And the results using this approach sound very robotic. The Performance RNN sequence format. The sequence file format used by the Performance RNN model is closer to the MIDI file format, since it keeps the information of other events besides the note on and note off. It extends the one hot vector length beyond the 88 keys of a piano roll to allow the representation of more events like time shift, velocity, etc. The neural network operates on a one hot encoding over these 388 different events. A typical 30-second clip of a song might contain over 1,200 such one-hot vectors. The Performance RNN sequence preprocessing. The MIDI file data is first converted to a protocol buffer to handle the data more efficiently. To create additional training examples, the preprocess applies time stretching and transposition. Each performance is divided in 30-second segments to keep each example of a small size. The model is still capable of generating longer performance without falling over. But of course, these performances have little to no long-term structure. Here we can see a MIDI file converted to a protobuffer. I also converted the protocol buffer to pandas to visualize it better. Here we can see all the columns with the data we're keeping for the melody. The Performance RNN model. The architecture of the model is based on a multi-layer LSTM RNN. Here we can see the three layers. Dataset creation process, from MIDI to sequence. Multiple MIDI files can be converted to a single file of sequences using the convert dir to node sequences process. The input and the output directory of the files have to be defined, and the recursive flag allows me to process all files of the directory at the same time. This process did convert the MIDI file to a protobuffer sequence, preprocessed the sequence, and created one hot encoding for the sequence. Dataset creation process. Train and test sequences. Once the sequences are created, they can be preprocessed and separated in train and test data using the Performance RNN create dataset process. The input file name and the output directory of the sequence have to be defined. The model configuration indicates how to do the sequence preprocess, and the ratio indicates the percentage of the data used for evaluation. This process did preprocess the sequence, separated the data in train and evaluation, and did encode the sequence as one hot. Training the model. Once the train sequence is ready, training can be done calling performance RNN train process. The run directory has to be indicated, as it will be used to save the weights metadata and checkpoint information. The model configuration indicates the model configuration for training, and the training steps number indicates the number of epochs to train. The name of the training sequence has also to be provided. This process did train the model with a batch size of 64, RNN layers of 512 by 512 by 512, a drop keep rate of 1, a learning rate of 0.001, use the Adam optimizer, and a categorical cross entropy for calculating loss. It did save the history metadata and checkpoints and created the model graph. Here we can see how the training was done for many hours and up to 882 epochs. I did train the model during several days up to 882 epochs. I was not able to leverage the use of the GPU in Colaboratory, since the execution failed when the GPU was added. Usually these kind of music sequence generators take long time to train, at least 2000 epochs. Evaluating the model. Once the train is complete, the model can be evaluated with the performance RNN train process. The same parameters as in the training have to be used, plus the evaluation flag to ensure that the weights are not changed, and the sequence is used only for evaluation. This process did test the model and save the evaluation data. Accuracy of the model. As you can see here, the accuracy of the model started very low and improved as the model was trained, slowly and little by little. The loss improved also, slowly as the training continued. Generating music. Once the model is trained, it can be used to generate music with the performance RNN generate process. The run directory has to be indicated. It will be used to read the weights metadata and checkpoint information. The model configuration indicates the model configuration for predicting. The number of steps indicate the size in seconds of the melodies to generate. 3000 steps equals to 30 seconds. The output directory has to be indicated and also the number of songs to generate. A primer seed can be given in the form of a note, a song, of a series of notes. This process did use the model to predict and did generate 10 songs of 30 seconds. These are the songs I have generated so far. Creating a bundle of the new pre-trained model. Once the model is trained, it can be used to create a self-contained bundle as a package with the performance RNN generate process. For this process, the run directory has to be indicated. It will be used to read the weights metadata and checkpoint information. The model configuration indicates the model configuration to save. The file name of the new bundle has to be indicated, and also the flag to save the bundle. This process did create a model package and did save the bundle with the indicated file name. Generating music with the new bundle. Here is an example of a program to generate music using the new package bundle. Performance with Dynamics 882. Generating music with the original pre-trained model bundle. The same program can be used to generate music with the original Magenta model bundle, just changing the model name. Conclusions. Pros. The music generation with the Performance RNN model looks very promising. The resulting musical pieces have a more human sound. Google Magenta is a nice effort to integrate machine learning and deep learning with human creativity. Google Magenta tools can be used on Anaconda as well as in Colaboratory. Actually, it is easier to configure the Colaboratory environment. Cons. Google Colaboratory failed when GPU was added to train the model. Usually, these kind of music sequence generators take long time to train, at least 2000 epochs. The Magenta libraries are encapsulated, and the models cannot be accessed directly or modified. The documentation on the Magenta libraries is almost inexistent, and since the creation of the Performance RNN is very recent, there are no other examples or any other source of information. Lessons learned. There is almost no documentation about the Magenta's Performance RNN, but hopefully this document will serve as the first tutorial guide. References: Google Magenta and Yamaha ePiano competition website. Thank you for your attention.